Hello and welcome to my lecture series for Control System 1, and this course is for 5th semester BTech in Electrical Engineering students. Myself Suman Ghosh as a course coordinator, assistant professor from Department of Electrical Engineering, Guru Nanak Institute of Technology, Kolkata. This particular PPT is designed for lecture 11 and lecture 12. Today is our 11th lecture. Today we will start a new module, that is time domain analysis, where time domain analysis of a standard second order control system is present, and there are determination of time domain specification of systems, step and impulse response of the first and second order system, stability by pole allocation, Routh-Hurwitz criteria and its applications, and there is another more thing, that is control action, and in that particular topic there is PI, PD and PID controller, and there are steady state error and error constant, where P in PID, P is the proportional, I is the integral and D is the differential. So in our 11th lecture, that is in our today's lecture, we will discuss on time response analysis of a control system, transient and steady state response, type and order of a system, step, ramp and impulse response of a first order system, step response of a standard second order system. And in our 12th lecture, we will discuss on transient response specifications of a standard second order system, steady state error and error constant, and some more related workout examples on transient response specification of a standard second order system. So moving to our next slide, that is time response of a control system. Now we can analyze the response of a control system in both time domain and as well as in frequency domain. Okay, so if the output of the control system for an input is varies with respect to time, then it is called time response of a system. And the time response of a control system is generally two parts, that is transient response and steady state response. And before going to transient response and steady state response, let us talk what is transient state and what is steady state for a particular system. Let us take one example, that is in our room, suppose a fan is first in switched off condition, and then you just turn the switch on, then the fan will start rotating from 0 speed to a constant speed. So from 0 speed, just look at the figure, from 0 speed to constant speed. So in between 0 speed and constant speed there is a region. So that region is called transient state. And after, when the speed of the fan reaches to a constant speed, then it goes to steady state value. So this part is particularly for steady state value. So this is transient part and this is steady state part. So mathematically, a time response of a system, total time response of a system, can be expressed as small ct, t, where c is the time response and T. So Ct is equal to CTRT. CTR means transient response plus CSS, that is steady state response. So total response, so total time response of a system is the sum of time response in transient state and time response in steady state. So what is transient response? So after applying input to the control system, output takes certain time to reach its steady state value. So if the output will be transient state till it goes to a steady state value. Therefore, the response of a control system during the transient state is known as transient response. Now, if the t, that is the time, tends to infinity, then we can neglect the transient response. So mathematically, we can write limit t tends to infinity, CTR is equal to 0. That means if t tends to infinity, that is the value of t is very large, then we can neglect the transient response of a system. Now, what is the necessary or what is the importance of the transient state? The transient part of the response reveals the nature of the response, that is whether it is oscillatory in nature or whether it is overdamped in nature, and also gives an indication about the speed of the system or speed of the process. Next, moving to our next slide, that is steady state response. The part of time response that remains even after the transient response has zero value. Okay, for large value of t, then it is known as steady state value. Actually, steady state means after transient state, the response of the system is constant at a certain value. That value is considered as steady state response. That is, this is our transient part, this is our transient part, and after transient part, the output of the system got fixed. So this is our steady state response or steady state part. Now, what is the importance of steady state response? The steady state part of the time response reveals the accuracy of the control system. Now, what is steady state error? Steady state error is basically the difference between the applied input, that is reference input, to the controlled output, that is CT. That is the difference between RT and CT. The steady state error is observed if the actual output does not exactly match with the input. That means it is the difference between the actual response to the input of the system, that is RT minus CT. Now, before going to our main topic, that is time response of a second order system or a first order system, we have to know some basic standard test signals. So first is step signal. Now first is step signal. Step signal is a signal which changes its level from one to another in a very short time. Just look at the figure. Here, the response starts from the origin and goes to a high value within a very short time. So we can write this, or we can draw this type of figure like this, neglecting the transient part. So this is our step signal, and it is represented by Ft is equal to A ut, where ut is the step response, where ut is the unit step response, where ut is the unit step response. So we can write Ft is equal to A as ut is equal to 1. So step response is basically a straight line. Now next is ramp signal. Let's look at the figure. This is the figure of a ramp response or a ramp signal, and the ramp response is given by Ft is equal to At ut. Okay, now just go to our previous topic, that is step signal, and our step signal is Ft is equal to Aut in time domain. Now if we consider, or if we apply Laplace transform here, and then we can go to in our frequency domain, that is Fs is equal to A by S. Now in case of ramp signal, the time domain response is Ft is equal to At ut, where A is the slope of the system. Now if we apply Laplace transform, then Fs will be A by S square. So this is our ramp signal. Now next is parabolic signal. This is our parabolic signal, and our parabolic signal is expressed in time domain like Ft is equal to t square by 2. Now if we apply Laplace transform here, then we can get Fs is equal to 1 by s cube. So parabolic response in Laplace domain will be 1 by s cube. And next is our impulse signal. Now what is impulse signal? Impulse signal means in a certain value of t there will be a high value or high magnitude, and the other part of the t, the magnitude will be remain 0. So this is our impulse signal, and at t is equal to 0 there will be a high magnitude, and in other part of del t the value of Ft will be 0. So Ft is equal to delta t. We can write impulse signal as delta t. Now if we apply Laplace transform here, then we can get Fs is equal to 1. Okay, so this is our impulse signal. Now another very important topic, that is type and order of a system. Now suppose a transfer function is given to you and you have to find the type and order of a system. Then how can we find the type and order of a system? Now in our previous lectures we just know how we can calculate the number of poles of a system. Okay. Now if we consider this transfer function gs is equal to 5 by s minus 1, from this if we want to calculate poles of a system, then we have to see the denominator part, that is s plus 1. If we put the denominator part s plus 1 is equal to 0, then if we calculate s, then we get s is equal to minus 1. So at s is equal to minus 1, there will be a pole. So for this particular transfer function, there is only one pole, and that is at s is equal to minus 1. So if we want to calculate the order of a system, then we have to see the numerator and then we have to see the denominator part. And the higher value or the higher order of the denominator, that is our order. The highest power of s in the denominator of a transfer function indicates the order of a system. So if we consider this equation, then highest power of s is 1. So order of the system is 1. Now what is type? The number of poles at origin of any system indicates the type of a system. So if we consider this, there will be only one pole, and that is at s is equal to minus 1. So there is no poles at s is equal to 0. That means at origin there is no poles, or at origin there is 0 poles. So the type of the system is 0, and the total poles present in the system is 1. So that's why order of the system is 1. So if we take this example, then we can see from this that the number of poles present in the system is 2. So total number of poles present in the system, mind it, present in the system, not in the origin, present in the system is called order, or the highest power of s, that is s square, that means 2. So the order of the system is 2, and the number of poles present in the origin, that is called type. So here 2 poles are present. One is at s is equal to 0, that is origin, and one pole is at s is equal to minus 1. So there is one pole at origin, so the type of the system is 1, and 2 poles present in the system. So that's why order of the system is 2. Now if we take this example, then we can see total number of poles present in the system is 3. 2 poles present in the origin and 1 pole present in minus 1. That means total 3 poles present in the system. That's why the order of the system is 3. But there are 2 poles, only 2 poles are present in the origin. That's why type of the system is 2. So it is very important. Total number of poles present in the origin, that is our type, and total number of poles present in the system, that is our order. Now moving to our time response of the first order system. Why it is called first order? Now if we consider this example or this uh, forward path transfer function, then we can see there is only one poles, and the highest power of the denominator is 1. That's why it is called first order system. Now there is a feedback with unity. That means there is a unity feedback. Hs is equal to 1 and Gs is equal to 1 by St. Now if we apply a closed loop transfer function formula here, which is Cs by Rs is equal to Gs by 1 plus Gs into Hs. And in this particular problem, Gs is equal to 1 by St and Hs is equal to 1. Just put the value of Gs and Hs, then we can find like this. 1 by t by s plus 1 by t. So this is our closed loop transfer function. Now, what is impulse response of a first order system? Now, if we want to calculate the impulse response, then we have to give a impulse signal as a input, that is RT is equal to delta t. Now, if RT is equal to delta t in time domain, then Rs will be in frequency domain, that is 1. That means we have to apply Laplace transform here. So Rs is 1. So if we apply Rs is equal to 1 in this equation, then we get Cs is equal to 1 by t in divided by s plus 1 by t. Now if we apply inverse Laplace transform here, then we can get the time response, that is Ct. Now if we apply inverse Laplace transform for this equation, then we get Ct is equal to 1 by t e to the power minus small t by capital T. This is our time response or impulse response of a standard first order system. Now, what is the nature of the impulse response? Now, from this equation, if we want to calculate or if we want to draw the nature of the system, then just put the value of small t from 0 to infinity, and for small t is equal to 0 to infinity, there will be lots of value or infinite number of values of Ct. So just put the values of t versus Ct. Then we can get the impulse response like this. And at small t is equal to 0, the value will be maximum, and that will be 1 by t. And small t is equal to capital T condition, the impulse response or the magnitude will be 36.8% of the maximum magnitude. Next is time response of the first order system, that is step response. Step response of a first order system. So this is our transfer function of a standard first order system, which I already discussed in our previous slide. So this is our closed loop transfer function of a standard first order system. Now if we want to calculate the step response of the first order system, then we have to apply the input as a step input, that is RT is equal to UT, unit step input. If RT is equal to UT, then RS will be 1 by S. Then RS will be 1 by S. Now put the value of RS in this particular equation, then CS will be like this. Just multiply RS in this equation, RS in this equation, and put the value of RS as 1 by S, and we can get like this. And if we apply partial fraction method, then we can get, after partial fraction method, like this, 1 by S minus 1 by S plus 1 by T. That is our CS. Now if we apply inverse Laplace transform for this equation, then Ct will be like this. Then Ct will be 1 minus e to the power minus small t by capital T. Now if we want to see the nature of the step response, just look at the response. This is our steady state value or maximum value, that is 1 or 100%. That is 1 or 100%. And at small t is equal to capital T, the magnitude will be 63.2% of the maximum or steady state value. 63.2% of the steady state value. Next is ramp response of a first order system. Now, what is ramp response? Now, for a closed loop standard first order system, the closed loop transfer function will be like this, which I already discussed in our previous slides. Now, if we want to calculate the ramp response, then we have to apply a ramp input. So the ramp input will be RT is equal to TUT, where UT is the unit step response, and the value of the unit step response, that is UT, is equal to 1. So basically UT is equal to 1. That means RT is equal to T. Now if we apply Laplace transform here, then we can get Rs is equal to 1 by S square. So this is our ramp response in S domain. Now, if we put the value of Rs in this particular equation, then we can get Cs is equal to like this. Then Cs will be 1 by T divided by S square into S plus 1 by T. Okay, so if we want to calculate ramp response, then we have to apply here inverse Laplace transform. So for this equation, if we want to apply inverse Laplace transform, then we have to apply partial fraction method first. So if we apply partial fraction here, then it will be like this. That is 1 by S square minus capital T by S plus capital T by S plus 1 by capital T. So if we apply inverse Laplace transform for this equation, then it will be like this. Ct is equal to small t minus t plus capital T e to the power minus small t by capital T. Now, in our previous slide, we already discussed what is error. Error means the difference between the reference input and the actual output. That means RT minus CT is our ET, error signal. So if we put, so in this ramp response calculation, what is RT? RT is T. As UT is equal to 1, so we can write RT is equal to only T. So RT is equal to T. Now what is the value of CT? We already calculate CT is equal to T minus T plus capital T e to the power minus small t by capital T. Just put the value of CT, then we can find the error signal like this. That is T capital T into 1 minus e to the power minus small t by capital T. That is our error. Now what is steady state error, or when we get our steady state error? At t tends to infinity, we get our steady state error. So limit t tends to infinity, et will be our steady state error. So if we apply t tends to infinity for this equation, then we can get only capital T. So our steady state error will be capital T. So this is our steady state error. If this is our ramp signal, input, and this is our output response CT. So the difference between input signal, that is RT, and the output signal CT is known as steady state error at t tends to infinity, which is capital T. So moving to our first example. Suppose there is a problem for a system shown in figure. Find out the step response of the system. Also find out the steady state error for that system. So there is a closed loop system. We have to find the closed loop transfer function first here. Then we have to calculate the steady state error. Very simple. Here the forward path transfer function gs is equal to 2 by s plus 1, and the feedback path transfer function hs is 1, as there is unity feedback. So if we apply the formula of the closed loop transfer function, then we can get cs by rs is equal to gs by 1 plus gs into hs. Okay, so cs by rs is equal to 2 by s plus 1 divided by 1 plus 2 by s plus 1. So here we can get the closed loop transfer function like this. 2 by s plus 3 is our closed loop transfer function. And for step response, rt is equal to 1. So rs is equal to 1 by s. Just put the value of rs in this particular equation, and we can get, after applying Laplace transform and after applying partial fraction method and inverse Laplace transform, you can get ct is equal to 0.667 into 1 minus e to the power minus 3t. That is our response, that is our output response or step response. Now if we want to calculate the steady state error, then we have to calculate first just the error of the signal, and the error signal will be et is equal to rt minus ct. Just put the value of rt and ct. Rt is equal to 1, as it is a step input, unit step input. So RT is equal to 1 and CT is this equation. So after applying RT and CT value, we can get ET is equal to, that is the error signal, is equal to 0.333 plus 0.667 e to the power minus 3t. Now what is steady state error? We have to apply limit t tends to infinity here. So limit t tends to infinity et is our steady state error, and that will 0.333 second. So this is our steady state error. So that's all for today's class, and in our next class we will discuss on step response of a standard second order system. Just move to our content page, and in our next class we will discuss step response of a standard second order system, transient response specifications of a standard second order system, and what is steady state and error, and what are the error constants. There are 3 types of error constant are there. We will discuss in our next class, and some workout problems which is very important for our semester exams. So in our next lecture, that is lecture 12, we will discuss last 4 part of this content. So thank you so much. Thank you for watching.